Hello everyone! Today we're going to discuss the rectangular components of a force in an inclined plane. An inclined plane, also known as a ramp, is a flat supporting surface tilted at a specific angle with one end higher than the other, used as an aid for raising or lowering a load. Here is an example of an inclined plane. There are at least two forces acting on an object in an inclined plane. First is the normal force and second is the force from gravity. The normal force is defined as the force that any surface exerts on any other object. Normal force will always be perpendicular to the inclined surface. Here's an example of the normal force exerted in our object. Weight or force from gravity is an attractive force that exists between all objects with mass. It is always straight down, as seen in the given diagram below. The weight can be resolved into two components. First is the force aligned parallel to the inclined plane. Second, the force is perpendicular to the inclined plane. To solve related problems involving an inclined plane, it is much easier to redefine the x-axis to line up with the inclined surface and the y-axis to be perpendicular to the inclined surface, as you can see here in the given figure. This makes the parallel component of the weight in x direction, and this makes the perpendicular component of the weight and the normal force in the y direction. The angle between the weight vector and the new y-axis is the same size angle as the incline. To understand it fully, we're going to apply geometry and trigonometry on our given figure. From our basic knowledge in trigonometry, we all know that the sum of all the angles in a given triangle is 180 degrees. So if this is theta here, then this is a right angle, so this means this is 90 degrees. So if this is theta, that means this is 90 minus theta. So this is the measurement for this angle here. Next is we're going to recall the basic knowledge in geometry. So if we do have two parallel lines and a transversal line, the measurement of this angle is just equivalent to this angle here. So this is what you call as alternate interior angles. So in geometry, alternate interior angles are equal. Going back to our figure and applying geometry here, so as you can see, this line in our triangle is just parallel to this line here, which is our force. And we have here a line, this one in our inclined plane, this will serve as our transversal line. So based on geometry, if this angle is 90 minus theta, looking at our figure, the equivalent alternate interior angle is this angle here. So that is why the measurement of this is also 90 minus theta. If this one here is 90 minus theta and this one here is a right angle, that means this is 90 degrees. So that means this angle here is theta. To solve for the perpendicular component along the y-axis and its magnitude, we need to use trigonometry. As you can see, this line here is just adjacent to our given angle, which is theta, so we're going to use cosine. That's why the perpendicular component along the y-axis is equivalent to FG multiplied by cosine theta. To solve for the parallel component along the x-axis and its magnitude, we need to use trigonometry. So as you can see, this line here is just opposite to our given angle, which is theta. That's why we're going to use sine. Therefore, the parallel component along the x-axis is given by FG multiplied by sine theta.
If you find this video helpful, please consider subscribing to show your support so that I can make other videos like this.
To understand what we have discussed, let's have an example. A block of 1,000 Newton kept on inclined plane is pushed by horizontal force 500 Newton. Find the sum of the components of forces along x and y axes oriented parallel and perpendicular to the incline. Please refer to the figure below. Let's have an illustration of the component of forces of W. It's easier to solve this if we have an illustration of the given figure. So if we're going to look at our weight W, as you can see, it is going downwards. If we're going to get the components of our W, take note that our X and Y here is tilted on a specific angle. So in this case, our X will be in line with our inclined plane, which is 36 degrees. So if this is our weight W, drawing a line which is parallel to our incline, we have this, which is WX, and drawing a line perpendicular to our incline, so this will serve as our WY. Solving for WX, as you can see, WX is at the opposite side, so we're going to use sine theta. Given W is equivalent to 1,000 Newton, we have Wx is equals to W multiplied by sine theta. Substituting the given for W, which is 1,000, and we have theta, which is 36, so we have Wx is equals to 1,000 multiplied by sine 36 degrees. Using our calculator to compute for our Wx, we have Wx is equivalent 587.78 Newton. Take note that the sign convention here is negative because as you can see, Wx is located at the negative part of our x-axis. Solving for our Wy, as you can see, Wy is at the adjacent side of our angle. That's why we're going to use cosine theta. Given W is equals to 1,000 Newton, we have Wy is equals to W multiplied by cosine theta. Substituting the values, we have W equivalent to 1,000 and theta which is equivalent to 36 degrees. That's why we have Wy is equals to 1,000 multiplied by cosine 36 degrees. Using our calculator to compute for our Wy, we have Wy is equivalent to 809.02 Newton. Take note that the sign convention here is negative because Wy is located at the negative part of our y-axis. Let's have an illustration for the component forces of our F. Making a line parallel to our inclined plane, we can have our f of x. Take note that this line here is just parallel to this line, so that means this is also f of x here. Making a line perpendicular to our incline, we can have our f of y. Solving for our f of x, as you can see, f of x is at the adjacent side of our angle. That's why we're going to use cosine theta. That's why we have f of x is equals to f multiplied by cosine theta. Take note that our f here is equivalent to 500 Newton and our theta is equivalent to 36 degrees. That's why we have f of x is equals to 500 multiplied by cosine 36 degrees. Using our calculator to compute for our f of x, we have f of x is equivalent to 404.51 Newton. Take note that the sign convention here is positive because f of x is located at the positive part of our x-axis. Solving for our f of y, as you can see, f of y is at the opposite side of our angle. That's why we're going to use sine theta. So we have f of y is equivalent to f multiplied by sine theta. Take note that our f is given to be 500 Newton and our theta is equivalent to 36. That's why we have f of y is equivalent to 500 multiplied by sine 36 degrees. Using our calculator to compute for our f of y, we have f of y is equivalent to 293.89 Newton. Take note that the sign convention here is negative because f of y is located at the negative part of our y-axis. Solving for the summation of forces in the x-axis, we have Wx plus Fx. Based on our calculation, Wx is equivalent to negative 587.78 Newton and Fx is equivalent to 404.51 Newton. Adding them, we have an answer to be negative 183.27 Newton. Solving for the summation of forces in the y-axis, we have Wy plus Fy. Take note that based on our calculation a while ago, Wy is equivalent to negative 809.02 Newton and Fy is equivalent to negative 293.89 Newton. Adding them, we had an answer which is negative 1102.91 Newton. That's all for today's video. I hope you learned something from this. Thank you for watching. Goodbye.